Alright, good morning, or whatever time of day it is where you are watching this right now. Let's take a look at Euclid's Book 1, Proposition 4. That is to say, if two triangles have the two sides equal to two sides respectively, and have the angles contained by the equal straight lines equal, they will also have the base equal to the base, the triangle will be equal to the triangle, and the remaining angles will be equal to the remaining angles respectively, namely those which the equal sides subtend. So it's a mouthful of words to say side angle side, which was probably burned in your head in high school. And we're just going to take a look at it through the lens I believe Euclid looked at it through 320 something BC, something or other. And that is essentially, I think he would have used his proposition 2, because that would have been one of his only tools at the time, and essentially just move this over to here and say, you know what? Good enough. Same thing. So he seems pretty stumped considering he wasn't down with using rotations or motions, excuse me, back when he was creating Proposition 2, but changed his mind. Yeah, difficult problem. And so we're going to try and extend this segment BC, the length of it, from this point B. And what that means is we're going to need to go from point to point here, create this segment, and we're going to need to, on this segment, construct an equilateral triangle. B to B, B to B. Alright, so now there's a point up here, up in the sky. You can mark that thing, make a little equilateral triangle happen. Very beautiful. And we're going to hide these circles because we're about to make a bunch of circles. Or if you're doing this by hand, you're going to have fun because you get to use a compass. It's my favorite tool. And now from here, if you remember the construction, if you did your homework, studied, we need these lines because they're going to help us out here in a minute. Now on these lines, we need to make marks or use circles, and we need to go from the point which we want to, what is the word? Move our segment from, and we're going to extend this out the way to this segment. So there's another radius line on this line, and we're going to mark that point whenever it ends up getting named H. Now we're going to create a circle with center G and radius H. And from here, if we observe this, we'll find there's another little point over here that you can create a circle from. And I'm going to claim that this circle with center B1 with radius BI is congruent to this circle with center B with radius BH. Reasoning for that is both of these segments GB and GB1 are congruent, and if you take these segments away from GH and GI, you're going to wind up with BH must be congruent to B1I, and therefore they're both radius of the same circle. So now that we know that these guys are congruent and C1 intersects this circle, and now you wouldn't know this in modern geometry because you wouldn't be able to assume it. I guess you would know it, but you couldn't assume it. But Euclid says, you know what, our compass lined this stuff up, must be the way it is. So that's where you kind of start running into flaws, if you're not already running into a circle flaws that Hilbert also had to deal with. And from this we can say, okay, well this segment must be equal to that segment, and we can mark them to show that that's truly how we feel. So we're going over their style. That's confusing. Something must be wrong with these. I have to hide some of this stuff. There we go. So now we should be able to. It's not going to let us. Whatever. I'll deal with that later. And then from this point, Euclid just kind of assumed these angles were the same, since honestly they look the same. That's just, I think that's good enough for him. Call it a day there. This is not a proof. best way to actually do this proof is to not. That's why Hilbert made it congruence axiom 6. All right, thanks for watching.